So, hello everyone. We're here to talk about serverless infections today. Serverless is something more and more way beyond the buzzword at the moment, and we need to make sure that we understand all the implications we're implementing that. So, about me, my name is Erez. I'm head of security research in Checkmarx. And this is usually the part of the talk when I need to justify why I'm allowed to sit here and explain things to you. So Checkmarx handles a lot of software exposure issues. Serverless is no different, and as part of my job, I see, and we see in general, a lot of mistakes done by developers, architects, etc. Usually these mistakes comes with reasons or excuses. Actually, we're here of making mistakes in serverless. So let's start. I will give a quick intro to serverless. By the show of hands, how many people here work with serverless as a day-to-day thing? Okay, that's quite a lot. How many use serverless at least once? How many people know what serverless is, although they're not working with it? Excellent. So yeah, so we'll make a quick intro, I guess. We're a specific focus on AWS Lambda of Amazon. Then we'll show some demos of what we did, moving from code injection to actual viral infection. We give a few more words about the AWS Lambda security, and then hopefully on time, we'll finish with some takeaways. So start by a legal thing. I understand it's illegal to talk about serverless now without at least showing this picture or a similar one, so here it is. Let's put it behind us and continue. Intro. Let's talk about evolution. A long time ago, I'm trying to convince myself it was not that long, but we had data centers. Data centers was hardware. Meant is that if you need more storage, you added a hard disk. You needed more computing power, you added a CPU. Generally, if you had more room for more servers, you need another room for the servers. Maybe that's better. After that, is it okay now? Okay, let me know if not. So the poly one? Turn off, okay. So after data centers, we got introduced to infrastructure as a service. AWS by Amazon was a really good, is really good example for that. You don't care about hardware anymore. The unit of scale is operating system. You need another one, just turn one on. Later, there was introduced a platform as a service, Salesforce Heroku, if some of you knows it. Know it is a good example for that, where you have the application as the unit of scale, and you don't care about anything below the application itself. And now the new era of serverless computing, where the unit of scale is actually the function, where you abstract everything except the code itself. This is all you are worried about. Let's look from the side of deployment, especially when considering time. When you had data centers, deployment could have taken months. The application lived for years, which means that if you had a problem, it was a very persistent problem. I'm talking about code vulnerabilities, of course. We then moved to virtualized cloud solutions and containers. Deployment improved from minutes to seconds. The processes lived for weeks, sometimes hours. But now we have the what's called function as a service. It deploys in, seriously, milliseconds. It lives for seconds, and then nothing is left. We can see the life cycle here. You actually develop a function, code, as any other function. You push it into a specific place in the cloud. Then something triggers it. We will talk about the triggers a bit later. And then it's cleaned. No traces of what happened, of the parameters, of the results of calculation, nothing. Everything is clean. Very short-lived. So the benefits. We can talk about scalability, and then we have two buzzwords, both serverless and scalability, which is great. But it is really scalable. When using Lambda functions, it doesn't really matter if you use one function, an instance of a function once a day, once a week, or you use 1,000, 2,000 instances of a function per second. It's not a problem. It's definitely not your problem as a user. It just happens. And it's very scalable and very comfortable. You don't have operation problems. You don't need to connect any wires. You don't need to update anything, no patches, no memory restrictions. It just happens magically on the cloud. These two things, the scalability and no need for operations, results in low cost. We didn't get really into that, but we hear it from a lot of customers. The model of pay for what you use, it makes everything cheaper. Also, the ability to move sometimes your work into less stressful times makes it even cheaper. So these are the benefits, and this is why the industry is going there. We also have the downsides. The downside, one downside is we see a new paradigm here. It's a problem sometimes for developers who needs to think a bit differently when they're implementing things. It's a problem sometimes for architects. They need to design their new systems in a different way, less stateful. I mean, it's more stateless. There's no classic back end anymore. And sometimes it's a problem for the companies themselves who have sometimes difficult, it's hard for them to move to new technologies and adopt new ways of work. It's also slower. There is sometimes some overhead when the code is pushed to the cloud in the beginning, and every time it's triggered, it needs to be pushed to a new container. Most services offer some sort of caching for that, but still, there is sometimes not big, but overheads, which makes the process slower, and this is something to think about. Monitoring is terrible. Monitoring is not really possible. You're moving from a place where you could log everything and monitor everything from one server or one batch of servers to a situation when the processes are not running on the same server, sometimes not even on the same continent. So monitoring is really tough, logging is really tough. This is one of the biggest issues at the moment that are try to be solved by the solution givers. And the last thing is the platform dependent issue. If you go and adopt Amazon, for example, as your platform, you will have really hard time later moving to Google or Microsoft or IBM, especially if you're using all the other services as well, for example, the S3 and buckets and all that. So it's kind of considered some sort of marriage to the specific platform, and it's not really easy to move. So these are the downsides. Let's see what we have out there today. We have the commercial solutions that most of you probably know. Google has one, Amazon, Microsoft, and IBM. Also many open source solutions, Function, Gestalt, Iron Functions. Each one of them has their own pros, their own cons, but it really shows that serverless is here to stay. It's adopted by both the server givers and users and vendors, and it's here to stay, for sure. We wanted to take focus on one specific solution because we wanted to create some demos, so we compared them. Compared to Google and Microsoft Azure, Amazon has the AWS Lambda. It's most common, it's considered relatively mature. It's here since 2014. They have a really wide language coverage, and we decided that our demo and our proof of concept will be focused on that. So let's talk about Amazon's Lambdas. They support a lot of languages, including Node.js, Python, Java, .NET Core. They introduced Go in the beginning of this year, which was really fun. And we can see that they have two ways of triggering functions. The Lambda functions, it can be either triggered explicitly by an API, just an API that calls the Lambda function and runs it, and also by using any other service by Amazon. It can be, as noted here, S3 update or IoT button, or the code commit AWS or CLI task, or whatever needed, you can use it as a trigger, which is extremely comfortable. The common use cases for that is a lot of mobile functionalities, backend not in the classical way, but in a serverless way. IoT backend, we see it a lot in bots and chatbots, scheduled tasks because of the triggering, anything that is really high consumption of CPU, file and image processing, distributed computing by fuzzers or machine learnings. Next time you need to crack a password, this is probably one of the best ways. And Alexa skills. So serverless is great, right? What else could we ask for? Well, security, and this is why we're here. When talking to developers, when we find problems in the code, for example, code execution or code injection, we often hear, yeah, but it doesn't matter because it's serverless. And when we say, so what? They say, well, there are two reasons. The first reason we hear a lot is that the potential damage is very limited. When the function is running on its own environment, very limited, we can even call it sandboxed, the potential of damage is very limited. The second thing is that the environment is disposed after run. We just saw that, right? So nothing is stored, nothing is persistent. You can damage very little for very little time, and that's it. This actually makes serverless the cure for everything security related. So no, actually not. We wanted to show it's not true because we started to get that a lot. We want to exploit a code injection vulnerability, something that many people would say it doesn't matter on serverless, in a Lambda function, and we want to create code persistent viral backdoor. This was the challenge. You can see below a link to a talk given by Rich Jones. This was one of the inspirations for what we did, and he has some more materials there. You should read it. So, challenge accepted. Let's see how we take a code injection and make it a viral infection. So, let me introduce you to the playground. Using AWS Lambdas, we build a very small and not complex 3 functions. One is main that calls 2 other functions. One is users, one is cars. I will show it to you if there are any UI people in the audience. I'm sorry, this is not our strong part. I said I'm sorry. Okay, so we can see the URL, it's being parsed by main. The resources, either cars or users, are here. You can see them here. And then we use a parameter to say which source we want. So if we take here, it was cars 1, we can see it. It's being called here, and then user 1 is here. This is how it works. Users 1 goes to users 2. Resource is user, parameter is 2. If you go to cars, this is actually what it's doing. Nothing else. Very basic, not very interesting, but it's a model of way, way more complex implementations out there. So what is a code injection? I love quoting OWASP, especially on OWASP events. So it's an attack type, which consists of injecting code that is then executed by the application. I'm pretty sure most of you know what it means. So we added a code injection, the same one that you can see here. So you can see that resources and parameters are parsed and concatenated into code. Both are based on input in the URL, and then it is run, the code by eval. Most of you should move uncomfortably when confronting this kind of code twice. Once is because it's probably the worst way to do that, and the second time is because we know that it happens a lot out there. We see it every day, and this is how code looks like. So we have a code injection, and the developer says that it doesn't really matter because nothing can happen. Again, very short-lived, nothing persistent. So let's see what we can find on this soon-to-die instance. We went to the documentation of Lambda. Lambda has a lot of internal environment info. We found one interesting, and it's called Lambda task root. It contains the path to your Lambda function code. That's it. This is the function where all your Lambda functions live. Not only the one that you currently see, but the entire tree. So this is rather interesting. And we tried that. We have prepared a payload for code injection. You can see the encoded and the decoded code here because we obviously used the encoded one, but I want you to see. So we use the resource cars, we use the parameter 1, and then we escape it and do whatever we want. We get the parameter Lambda task root, and this is what we got. Excellent. So we have the path of our task. Very simple, not very surprising, because actually var task is the default path, but it can obviously be changed and we can find it. So, okay, we can get some information about that. What if we actually can, now that we know this path, we can actually take all the information in it, all the functions. Maybe we can, I don't know, zip them or tar them and send them to our own place. So include just by checkmarks demo, we open checkmarks hack. And this is what we want to do. We want to be able, indeed it's short-lived, but we want to be able to look at the code later also. As attackers, it can be very useful to look at the code itself. So we did just that. Here's the payload. Again, the important parts are in red. You can see the compression here, and then we just curl it to our new home. This is it. It's empty at the moment. Now we go back to the demo, put the payload in successfully, and then when we refresh, we can see our atar. Opening it, we can see the entire thing, and actually immediately you can see some really important things in there. For example, the API key. You can lower your camera as we change the keys. So I see you there. You can lower it. We changed it before. But again, this is a very powerful thing to have, the API key. And you just got it by a very short-lived instance. So let's continue. What else can be done? This is nice, but it's not our goal. So back to documentation. Amazon is nice enough to offer some toolboxes for you. They offer you the SDK and the AWS CLI. CLI is less relevant here, but the SDK is very, very interesting. The SDK includes some functions that allows you, an API that allows you to list functions, to deploy new ones, update existing ones, and all of that is invoked by code. Now you have a small voice in your head telling you, yeah, but you probably need to be authorized, right? Yes, you're right. It only happens if you have permission authenticated by AWS profile. But you're also wrong, because when you're running the Lambda function, you've already been authorized. So an extra authentication is not needed. So every breach you have after the Lambda, every vulnerability you have after the Lambda actually started running has all the authentication needed. So this is nice. So let's update some functions. Now the reason we were so excited about it, because we didn't really know how we can make persistent vulnerabilities, because you don't have a database, you don't have a file system, you don't have anything. But actually, we're going to put our vulnerabilities, the persistency is going to be in the code itself. We're going to change the code and make it store the vulnerabilities. So you can see the update here. What this is doing, going over all the functions in the path. We don't even have to know which functions are there, just going through them, and then update them with our own malicious code that we'll see a bit later. Let's see how it goes. This is how it looks. And then we put the payload. Successfully. Yay. So just by running the payload on the cars, we can see that we infected both cars and main. Can you see that? The reason is, again, that we iterated over all the functions under the path and infected them. So this is pretty nice. All we did in the code was actually just adding strings, but you can obviously understand that if we change the code, we could change it to anything we want. So this is a serious thing. And we managed to get persistency, which is great, but it's a one-time infection. It's not really what we call a virus or viral infection. It's a one-time infection. If the function is cleaned or updated or anything like that, it will stay clean, and we don't want to reinfect all the time. Let's see how it's done. We implemented the reset function, and when we reset cars, we can see that main is still infected, but cars is not. So we had a new goal. The goal is persistent infection and cross-contamination. The reason we wanted to do this cross-contamination is that this way, each function actually checks the other functions, make sure it's contaminated. If it's not, reinfection. which causes viral infection with cross-contamination. So let's see the last demo. In this demo, we have, again, the main, cars, and users. Cars and main are clean. We inject the payload into users when main and cars are still clean. When someone loads users, it infects main and cars. Everything is now infected. It could be 50, 70, 1,000 functions. It doesn't really matter. And then we know that the user, developer, vendor, whatever, tries to clean them, but he forgets one. He forgets the car function. So again, when someone loads car, again, full infection. So let's see that happening. So here we have the payload. Successfully. Someone runs cars. It's clean, but when someone runs users, the infection takes place. You can see that users is already infected. Now we can check cars again and see it was also infected, including main. Now we do what we did before. We reset main. We reset users, but we forgot to reset cars. So everything looks fine now until someone triggers cars. It seems like only cars is infected, but if you go back to users, you can see that again, every function under this path is infected again. And voila, we have persistent code contamination in a non-persistent environment that can do whatever we want. Mission accomplished. Let's talk a bit more about Lambda security before we finish this. So a few more words. Lambda security depends on two main parameters, execution role and VPC. The execution role means whatever the function is allowed to do. You can get really into fine-grained permissions there if you know it and if you want to do that. VPC is which virtual private cloud the Lambda function belongs to and can communicate with. So if we're looking at execution roles, how many of you knows Claudia.js? Okay, I thought more. It's a pretty common solution for deployment of Node.js projects to AWS. Let's for a second look at the documentation. You can see that. AWS Lambda full access is required for all Cloudia deployments. So if anyone is using Claudia, and that's a lot of people, they're giving the full permissions as requirement. We thought Claudia is the only one, but actually we see it all over the place. Even Amazon themselves, they have a GitHub sample showing you how to use a single Lambda function. It's in their GitHub. This is the actual documentation of it. This is what they recommend to use. And they say prerequisite, create a role called Lambda role, assign it AWS Lambda full access. So this is the boilerplate for many, many other projects. It's being forked constantly. You can guess that if this is the documentation of Amazon, this is what is going on out there. The VPC, the virtual private cloud, is actually, there is no VPC by default. I remind you that if there was some sort of VPC, we could not even do the first step of exfiltrating data because we contacted something beyond what would be considered the virtual private cloud. So it's not, by default, it's not activated. We had a chance to talk with an Amazon engineer. This was kind of the reply. The main issue they have was with the documentation. They said they will change it. It was a year ago. It's still the same. But this is something that we need to understand. They consider it working as intended. You should not have issues in your code, and they are right. I think there are better ways to handle it, but they are right. Issues in your code are yours. This is the only thing they're not in charge of, and you should take care of that. So let me finish with some takeaways. Okay, serverless, but we still have two servers, and both of them can be attacked. One is the server that hosts the container, the running container. This is the one that we got the information from in the beginning. The next server is the server hosting the source code. This is the server that we attacked when we wanted to update the functions to malicious ones. We need to keep security in mind. Although it's not our business what Amazon is doing or not, we still need to be aware of sensitive data in our functions. It's really bad practice. We need to be aware of the role permissions that we give and VPC. All these things are solvable and should be handled. This is configuration. And the last thing, that should be also the first thing, you need to check the quality of your code security. There's nothing different between code that is going to the cloud, to Lambda, to any function somewhere, virtual as it may be, short-lived as it may be, sandboxed as it may be. There's no difference between that and classical code with vulnerabilities. And that is that. Thank you very much. Questions?
Do you know if there's specific functions that would be used with Lambda that would tend to be vulnerable that wouldn't be in other situations? So, I mean, if you're writing Python, you would call specific things. So your typical code scanner wouldn't notice it, and you have to look at specific things or build your own rule. I'm assuming most code scanners aren't Lambda code aware.
Well, actually, I'm from Checkmarks. I can say about us that we are.
Okay. Well,
I don't know about others. I guess some of them can integrate that as well. It's not supposed to be that difficult. There are no specific functions that I can say that are more vulnerable than others. The vulnerability itself is the problem, is the issue. It's the same classic vulnerabilities. We just need to change the way we think about serverless, about so short and so sandboxed, and just look at it as any other normal, regular vulnerability. And it doesn't matter the language as well. It's the same. It's just, well, I prefer not to talk about the product at the moment, but just regular scans. It just scans it automatically. Yeah.